In this lesson, we will focus on the comparison between planing and grinding techniques in Project 2, as well as the selection of cutting tools. We will particularly delve into the principles of grinding in Task 2.2. We will explore the basic concepts of grinding, the specific functions during the grinding process, the characteristics of grinding, and the calculation of relevant parameters. By comparing grinding with planing techniques, we aim to help you understand the unique value of each technology and cultivate a dialectical engineering perspective. In the field of metal cutting, planing and grinding are two important machining techniques. Planing is a traditional machining method that uses a planer to cut the workpiece. It is characterized by simple equipment and easy operation, making it suitable for machining relatively simple shapes and surfaces, such as flat surfaces and grooves, where precision requirements are not particularly high. Grinding, on the other hand, is a method that uses abrasive tools to process the surface of a workpiece, achieving higher machining precision and surface quality. Next, we will focus on explaining the principles of grinding. The basic concept of grinding. Grinding is a cutting process involving multiple small cutting edges. Abrasive tools, such as grinding wheels, are porous objects made from abrasive materials and bonding agents. The abrasives, which are very hard, act as cutting edges during the grinding process. Common abrasives include alumina types, such as brown alumina and white alumina, and silicon carbide types, such as black silicon carbide and green silicon carbide. Brown alumina is suitable for grinding carbon steel and alloy steel. White alumina is suitable for grinding hardened steel and high-speed steel. Black silicon carbide is suitable for grinding cast iron and brass. Green silicon carbide is suitable for grinding hard alloys. The grinding process. The grinding process mainly includes three stages: rubbing, plowing, and cutting. Rubbing stage. The abrasive grains begin to contact the surface of the workpiece. Due to the relatively large blunt radius of the cutting edges of the abrasive grains, they exert pressure and friction on the workpiece surface, but have not yet cut into it. This results in elastic deformation of the workpiece surface, generating a significant amount of heat during this stage. Plowing stage. As the abrasive grains continue to advance, the pressure on the workpiece surface increases, causing plastic deformation. The abrasive grains begin to plow grooves into the workpiece surface, and chips are extruded in the form of small fragments. At this point, the temperature of the workpiece surface rises further. Cutting stage. When the cutting force of the abrasive grains is sufficiently large, the grains penetrate the workpiece material, removing chips and forming a new machined surface. In this stage, the cutting action of the abrasive grains is most pronounced. Characteristics of grinding: high precision and good surface quality. Grinding can achieve high dimensional accuracy, generally reaching IT6, IT5 levels, and low surface roughness, RI values, can reach 0.8 to 0.2 micrometers. This is because the cutting edges of the abrasive grains are very sharp, and a large number of abrasive grains on the surface of the grinding tool simultaneously participate in cutting, allowing for micro-cutting of the workpiece surface. For example, in the machining of precision mechanical parts, such as aircraft engine blades and precision molds, grinding can ensure the dimensional accuracy and surface quality of the parts, meeting their usage requirements. High grinding temperature. During the grinding process, friction and pressure between the abrasive grains and the workpiece surface, as well as the deformation of chips, generate a significant amount of heat. The temperature in the grinding zone can exceed 1000 degrees Celsius. Such high temperatures can cause surface burns and annealing on the workpiece, affecting its surface quality and mechanical properties. To reduce grinding temperature, a large amount of cutting fluid is typically used for cooling and lubrication. Grinding wheels have a self-sharpening effect. During the grinding process, abrasive grains gradually wear down. When they reach a certain level of wear, the grains will detach under the cutting force, exposing new, sharp, abrasive grains. This allows the grinding wheel to maintain good cutting performance consistently. This self-sharpening effect is a key characteristic that distinguishes grinding wheels from other cutting tools. Grinding parameters and calculations. Grinding speed versus. This refers to the linear speed of the outer circumference of the grinding wheel. The calculation formula is V, S equals pi ds ns divided by 1000 times 60, where ds is the diameter of the grinding wheel in millimeter, and s is the rotational speed of the grinding wheel in revolutions per minute. For example, when the grinding wheel diameter ds is 400 millimeters and the rotational speed ns is 1800 revolutions per minute, substituting into the formula gives Vs equals pi times 400 times 1800 divided by 1000 times 60 is approximately equal to 37.7 meters per second. Workpiece speed weight. This refers to the circumferential speed or linear movement speed of the workpiece. It affects the grinding efficiency and the surface quality. Generally, as the workpiece speed increases, grinding efficiency improves, but surface roughness also increases. Depth of cut edge. This refers to the depth at which the grinding wheel penetrates the workpiece. It directly affects the grinding force and the grinding heat. As the depth of cut increases, both the grinding force and the grinding heat will correspondingly increase. Comparison of planing and grinding and their ideological and political significance. Planing has advantages such as low equipment cost and simple operation, making it suitable for situations where high precision is not particularly required, such as the rough machining of ordinary mechanical parts. In contrast, grinding, although involving relatively complex equipment and higher costs, can achieve high precision and high-quality machined surfaces, making it suitable for the machining of precision parts. This indicates that different machining techniques each have their own advantages and applicable scopes. In practical engineering, we should not blindly pursue high-tech methods. Instead, we should analyze specific issues based on particular machining requirements, workpiece materials, production volumes, and other factors to choose the most suitable machining method. At the same time, traditional planing technology also holds its irreplaceable value as part of the heritage of metalworking techniques. We should continue to develop and innovate modern machining technologies while preserving traditional techniques. Tool selection. In grinding processes, the selection of the grinding wheel is crucial. The choice of grinding wheel primarily considers factors such as abrasive material, grain size, hardness, bonding agent, and structure. Abrasive. Choose the appropriate abrasive based on the workpiece material, as mentioned earlier regarding the types of abrasives suitable for different materials. Grain size. Grain size indicates the size of the abrasive particles. The larger the grain size number, the finer the abrasive particles. Coarse-grained wheels are suitable for rough grinding, achieving higher grinding efficiency. Fine-grained wheels are suitable for precision grinding, achieving better surface quality. Hardness. The hardness of a grinding wheel refers to the ease with which abrasive grains detach from the wheel's surface under the action of grinding force. If the hardness is too high, the abrasive grains do not easily detach, which can cause the wheel to clog, increase grinding force, and raise grinding temperature. If the hardness is too low, the abrasive grains detach too easily, leading to rapid wheel wear and affecting grinding precision. Bond. The bond's function is to hold the abrasive grains together to form the shape of the grinding wheel. Common bonds include the ceramic bonds, resin bonds, and the rubber bonds, each suitable for different grinding applications. Structure. The structure of a grinding wheel indicates the proportional relationship between abrasive grain, bond, and pores. The larger the structure number, the more pores there are, providing greater chip clearance space, which is suitable for grinding soft materials or situations with a large amount of material to be removed. In this lesson, we focused on the grinding principles outlined in Task 2.2. We first explored the basic concepts of grinding, understanding that grinding tools are made from abrasives and bonds, with abrasives acting as cutting edges. We then learned that the grinding process includes 3 stages: rubbing, plowing, and cutting. Additionally, we discussed the characteristics of grinding, such as high precision, good surface quality, high grinding temperature, and the self-sharpening effect of the grinding wheel. We also mastered the calculation of grinding parameters, such as grinding speed, workpiece speed, and depth of cut. By comparing with planing technology, we understood that different techniques each have their irreplaceable value. It is important to develop a dialectical engineering perspective that analyzes specific issues without blindly pursuing high-tech solutions, while also recognizing the significance of preserving traditional techniques. Finally, we learned about the selection of grinding wheels in grinding processes, which requires a comprehensive consideration of factors such as abrasive material, grain size, hardness, bond, and structure. I hope everyone can further consolidate these knowledge points after class to deepen their understanding of grinding principles.